All right, we're going to start with the second part of chapter 1, and we start off with this term called acceleration. So, what is acceleration? You know that um, you know the difference between speed and velocity by now. So, speed is the rate of change of distance, and velocity is the rate of change of displacement. So you can have a velocity, and how do you represent velocities? We use an arrow mark to represent velocity. So that is velocity v1, and that is velocity v2. Obviously, this velocity is more than this velocity by the length of the arrow. The direction of the arrow is what tells you the direction of the velocity. So the way the arrows are oriented tells you which way the vectors are headed to. So this is a velocity v1, and that's a velocity v2. And if something changes its velocity from this to this, that means it is accelerating. On the other hand, if you have a velocity like this to start with, and then it reduces to this, that means it is decelerating. So deceleration is like slowing down, and acceleration is when it's speeding up. That's one way of looking at it. So what is acceleration? Acceleration is a rate of change of velocity. And when can velocity change? When can velocity change? When either the magnitude of the velocity changes, the size of the velocity changes, or the direction changes. So if I have a velocity going like this, and then if I have a velocity going like this, that is a different velocity because the direction has changed. So here also there is an acceleration because the velocity has changed. So whenever you have a change of velocity, then you have an acceleration. And what is acceleration defined as? Acceleration is defined as the final velocity minus the initial velocity over the time. Final velocity, whatever it is, minus initial velocity, whatever it was, divided by the time. Now, if something is going in a straight, now, what is the unit of velocity? Meters per second. So change of velocity is also meters per second. And then you have divided by one more second. That's why we write it as meters per second square. So the unit of acceleration is meters per second square. The unit of velocity is just meters per second. So you have meters per second gets you meters per second square. So for example, if something was going at 20 meters per second, and then you accelerate it and make it go at 50 meters per second, and it took a time of, let's say, t is 6 seconds for you to do this. So the acceleration is going to be the final velocity minus initial velocity over time, which is 50 minus 20 divided by 6. That's going to be 30 over 6, which is 5 meters per second square, in the same direction as it is moving. So if I call this east, then that's going to be east. So that is basically what we do for acceleration. Acceleration is the rate of change of velocity. So if you look into the textbook, so you can see the definition of acceleration given here. And acceleration is the rate of change of velocity, and delta v over delta t. Now the delta simply stands to indicate a small change in. So a small change in the velocity over the time taken, that gives you the acceleration. And this actually gives you the instantaneous acceleration because you're taking for a small change. If you do an overall change, like here, like in this example, you saw it was an overall change. This was a velocity at time 0, and this is a velocity at time 6 seconds. So the overall change is 30 divided by, gives you the average acceleration. Now, on the other hand, if you take acceleration as delta v over delta t, a small change in velocity over a small period of time, that gives you the instantaneous acceleration. So there's a difference between average acceleration and instantaneous acceleration. So when you take off your car from a stoplight, you are moving from one velocity to another velocity in a period of time. So your instantaneous acceleration is probably the best in the beginning, and later on, you may be going at a higher speed. And if you calculate the average acceleration, all you need is the final minus initial over time. Whereas instantaneous acceleration requires you to know how much change is taking place every fraction of a second. Okay, so here is an example of acceleration, and here is another example of acceleration. After a race, a runner takes 5 seconds to come to a stop. So if he's coming to a stop, the final velocity is 0. So you always take the final first minus the initial over the time. And the answer is negative 1.8 meters per second squared. The negative sign tells you it is a deceleration or a negative acceleration. So acceleration is the rate of change of velocity. So wherever velocity changes, there is an element of acceleration. The other thing you should also know here is, that I mentioned over there, is whenever you have something going in a circular path, when something goes around in a circular path, when it is here, so it's going around and around like that, when it is here, it is moving in this direction with that velocity. And when it is here, it is moving in that direction with a different velocity. It may be going with the same speed. Speed is probably the same, but the direction is changing, so the velocity has changed. So it may be uniform speed, but not uniform velocity. Why? Because the direction is changing. So the direction is changing continuously, therefore this velocity is different from this velocity, although the speed is exactly the same. So you may be going on a roundabout at 10 miles per hour and 10 miles per hour and 10 miles per hour, but your velocity is changing. So here also there is supposed to be an acceleration. Now to create an acceleration, if something is moving with a certain velocity and you want to make it go faster, you need to really apply a force. Without a force, you cannot accelerate an object. Similarly, when you're going fast and you want to slow down, you need to apply a force, the braking force. So when you apply a braking force, you slow down. So that causes deceleration. To cause acceleration or deceleration, you need a force. Now we know that this velocity is different from this velocity, which means there is an acceleration going on. And the acceleration that's going on over here is actually in this direction. So the velocity v1 changes to this velocity. That's because there's an acceleration in this direction. And we call that acceleration centripetal acceleration. It only happens in circular motion. So in circular motion, or whenever an object is attempting to go in a circular path, you will have centripetal acceleration, and the centripetal acceleration is towards the center. How do you know that it is going to the center? You can also check it out by using this equation. So acceleration is final velocity minus initial velocity over time. So if you know what is this, you should be able to figure out the direction of acceleration as well. So final velocity is that way, minus initial velocity. Now initial velocity is upward, so minus initial velocity is supposed to be downward. That's minus initial velocity. And so this is going to be your final velocity minus initial velocity. And so the acceleration is directed in this direction. So the acceleration is going to be this minus this divided by time. So the acceleration is directed like this. Watch. This is the direction, and that is exactly the direction here. You can see that. So the direction of acceleration is always directed to the center. So centripetal acceleration is always to the center in uniform circular motion. Now, when you say uniform circular motion, it is uniform speed. So in uniform circular motion, the centripetal acceleration is towards the center of the circular path. Now, what is needed to provide? What should provide a centripetal acceleration? So centripetal acceleration has to be provided by a force. Is to be provided by a force. And or any acceleration has to be provided by a force. So the centripetal acceleration is provided by a force towards the center. So to change the velocity from there to there must be an acceleration in this direction, and that acceleration is called the centripetal acceleration, which depends on how fast you're going. So it depends on how fast you're going, and it also depends on the radius of the path, the radius of the turn. So centripetal acceleration is given by this equation. These are all derived from a certain procedure, but the scope of the derivation is not required here in this syllabus, in this okay, so acceleration is v squared over r. V is the speed, r is the radius. This should be in meters per second, and this should be in meters. So to get the centripetal acceleration, this is what is needed. Now, centripetal acceleration has to be provided by a force, as I said. So there must be a force acting in this direction. So if you're taking a roundabout with your car like that, if you take a roundabout like that with your car, what provides the centripetal force or the centripetal acceleration? It is friction on the tires. The friction on the tires has to provide this acceleration. Now, if the friction on the tires could not provide this acceleration, we will not be able to make that turn possible. So instead, we'll just keep skidding and going straight. That's what happens these days. If the road is icy, you are expecting a certain acceleration depending on your speed and radius, but what happens is the friction says, I give up, I cannot provide this much, and therefore you cannot continue making that circular path. You just skid off in that direction. So friction is a very important element between the tires and the road to provide the centripetal acceleration whenever you want to take a turn. Or even for that matter, when you walk around a curve, you need the friction, the grip on the ground in order to make that turn possible. So centripetal acceleration has to be provided to anything that is turning around. If you're taking the Earth and the moon is moving around the Earth, and the moon has to be provided with a centripetal acceleration, otherwise it cannot change directions. And what provides that is the gravitational force. the gravitational force between the moon and the earth provides a centripetal force for the moon to go around and around. What about the electron around the nucleus? The electrical force, the electrostatic force takes it round and round. So you should be able to recognize what force is taking an object round and round. Suppose I take a stone, tie it to a string, and just whirl it round and round. So if I take a stone and tie it around and then turn it round and round, the string is pulling the stone inwards, and the tension in that string provides the acceleration. Now, one thing you should notice in the acceleration is that speed is getting squared. So centripetal acceleration is v squared over r. The speed is getting squared, which means if you double the speed, the acceleration will become 4 times bigger. Because when you double the speed, say for example, if you were going at 10 meters per second, and the radius is 5 meters, then the acceleration is going to be 10 squared over 5, which is going to be 100 over 5, which is 20 meters per second squared. Whereas if I double the speed, then acceleration will become 20 squared over 5, which is 400 over 5, which is going to be 80 meters per second squared. So you can see that it goes 4 times bigger because the velocity is doubled. So double velocity square is actually 4v squared. So you can see the factor that's coming in is 4. So the acceleration depends heavily on the speed. So when you're taking a turn on a icy road, the best thing to do is to slow down. So if you slow down to half the previous speed, you're going to cut down the acceleration by 4 times. And depending on the road conditions, you may have to slow down pretty well. So if you slow down to half the speed, acceleration is cut down by 4. If you slow down to 4 times slower, instead of going at 10 meters per second, you go at 2.5 meters per second, then you are going to cut the acceleration down by 16 times. So the acceleration equation should be carefully done. I'm taking it back again to this textbook. So the centripetal acceleration is described here. You can see the velocities changing directions, and you can see the change in velocities in this direction towards the center. So you can see the equation is mentioned here, and here is an example of a car going around a curve, and see how it is solved. And and that is a tension in the string. So when this goes round and round, there's a string that's pulling it inward, providing the centripetal acceleration. And here it is. When you take a ramp, you can see how the radius of the ramp makes a huge impact. So you're going a certain speed, and the radius of the ramp. So something has to provide the centripetal force for you to go around the circle, and friction cannot be always dependent on. And if friction is actually kind of used, the tires can get worn out. Therefore, the ramp itself is banked. So when you bank the track, then you are able to provide an inward force to the center. And that's the reason why there's banking of tracks. So roads are banked, so you don't have to tilt your car. So if you're riding a bicycle, you can tilt your bicycle. But if you're riding a car, you cannot tilt your car. And therefore, the road itself is banked to provide the required centripetal acceleration. So you can see that part of it here. So this one kind of breaks it down clearly. You should go through this table and find out. Now let's go to the simple types of motion. The simple types of motion. Motion, so when objects move, they go through different displacements in different times. And so I'm going to show you a couple of graphs, because most of these things can be plotted on a graph to explain what's happening. So if I'm going to plot a graph of distance and time, if I plot a graph of distance and time, and if I draw a straight line like this, what does that imply? The straight line implies that you are at rest. You're not moving, because the straight line implies, let's say this is 0 meters, and that is 10 meters, and that is 20 meters. This means that at 0 time you're at 10 meters, at 1 second you're at 10 meters, at 2 seconds you're at 10 meters, at 3 seconds you're at 10 meters, which means you're not moving from that location. So this means at rest. Now what does this mean? This means here you are at 0 meters, after 1 second you're gone somewhere, after 2 seconds you're gone further, after 3 seconds you're at 10 meters, and so on. So this means you're moving at a constant speed, because you're moving through the same displacements in the same intervals of time. That's constant speed. Now what is the difference between this constant speed and this constant speed? The difference between the two constant speeds is that over here in 2 seconds you're reaching 10 meters, whereas over here in 3 seconds you're reaching 10 meters, which means this is faster. It's a constant speed and it's faster. And how do you know if it's faster or slower? It is the slope of the line. So the slope of the line gives speed. Slope of the line gives speed. Now what does this line mean? This line implies that the speed is increasing. Speed is increasing, and this line implies decreasing speeds. And what does this line imply? That line is impossible. Why? Because you cannot undo a distance that you already done. So according to this line, it says at 0 seconds you had covered already something like 18 meters, and after 1 second you seem to have only covered 17 meters. After 3 seconds you are back to 0, which means you have not covered any distance. Remember, distance cannot be undone. Like, you cannot walk back and say that I didn't travel any distance. So you keep traveling more and more whichever direction you move. So distance is something that cannot be removed. You can only do more and more distance by moving backwards. So this line is an impossible line on this graph. Now compared to this, the next graph I'm going to draw is for a displacement time graph. Displacement time graph. So on a displacement time graph, a line like this implies what? Again, at rest. A line like this implies what? It's a constant velocity. Remember, this is displacement measured in meters. So rate of change of displacement is velocity. So this implies constant velocity. And what does this imply? Higher constant velocity. That's a higher constant velocity. And this means it's increasing velocity. And that means it's decreasing velocity. And what about this line? And that line is possible. This means negative velocity. Negative constant velocity. You remember, velocity is a vector quantity, so you can have a positive velocity and a negative velocity. When you say negative velocity, it means like you're kind of returning back. That's a negative velocity. So you can have displacements going downward as well. So you can have a negative displacement, because displacement also is a vector quantity. So you can have displacements on the negative side. So you can have graphs even on this side, because displacement is a vector quantity and so is velocity. So what does the slope of this line give you? Slope of line gives velocity. So over here it's a smaller velocity, and over here it's a higher velocity because the slope is increasing. So the slope is increasing from this point to this point, so definitely this is a higher velocity and this is a lower velocity. The next graph is going to be acceleration. Oh no, velocity. Velocity time graph. Now when you have velocity time graph, a line like this implies constant velocity, like 0, 5 meters per second, 10 meters per second speed, 15 meters per second, and that will be 0, 1, 2, 3, 4. So this means constant velocity. You're moving at 10 meters per second here, at this time also 10 meters per second, at this time also 10 meters per second. So that's a constant velocity. And this line implies constant acceleration. So you can see that it's a continuous increase in velocity. So the velocity is changing. At 0 time it is nothing. After 1 second it's going here, at 2 seconds it's going here, 3 seconds it's going here. So the speed is increasing continuously, which the velocity is increasing continuously. So that is constant acceleration. So slope of the graph gives acceleration. So this obviously means higher acceleration. And this means increasing acceleration. And this means decreasing acceleration. And why do you say it's decreasing? Because the slope here is pretty high and the slope here is lower. So slope is rise over run, and the rise over run here is high, the rise over run here is low. So slope is low, so decreasing acceleration. So you can have negative velocity or negative acceleration. If it comes down like this, it's a negative acceleration. Negative acceleration. So that's a negative acceleration as it comes down, because it was a higher velocity and then it starts coming down to lower velocity. And according to the equation for acceleration, final velocity minus initial velocity over time, you can see clearly it is a negative acceleration. So hope this graph kind of explains to you what exactly is happening. So you should be able to plot a graph for any situation. Now what else can we get from the graph? From the graph we can get a lot of information, especially from the velocity time graph. So if for example something is moving at a constant velocity v for a period of time t. How far did it travel? So, for example, if it's 1, 2, 3, 4, and 5 meters per second, and 10 meters per second. So if it moved at 10 meters every second for 4 seconds, how far did it travel? It travels 10 meters every second for 4 seconds. And so it's 10 times 4 is 40 meters. So the area of this portion gives displacement. So displacement is equal to velocity times time, and this is only for uniform velocity. So displacement is velocity times time. We symbolize the displacement with the letter x or d. You can use any letter you want. So let me use d. So d is equals to vt. Displacement is velocity times time. Now, if this graph is like this, if the velocity time graph is not in this fashion, but if it's like this, then the area of this portion is going to be half of the entire area. So if you're starting with the velocity this, if you're starting with the velocity 0 and then going on with the to final velocity vf, the area of this part is going to be the displacement. And in this case, the area is going to be 0 plus this divided by 2. So half of the rectangle's area. So in short, we have a couple of equations to deal with. And those are called the equations of motion. And the equations of motion are derived by using the acceleration equation. So one of them is this, the acceleration equation. That is one of the equations of motion. And another equation of motion comes from the area. And so starting with the acceleration equation, acceleration is Vf minus Vi over time. If I cross multiply this, we get Vf minus Vi is equal to At, or Vf is equals to Vi plus At. So that's considered one of the equations of motion. You can actually learn a lot of things about the motion by connecting these variables. So that is one equation of motion. There's another equation of motion, which is displacement d is equals to final velocity minus initial velocity over time, over 2 times time. So displacement is going to be final velocity minus initial velocity over 2 times time. Now this is another equation of motion. Now just to let you know, for your exams, you can write these equations down on a note card and you can take the help of it during the tests. You're not expected to memorize these equations. Sorry, this is a plus. You're not supposed to, you don't have to memorize these equations. So displacement is Vf plus Vi divided by 2 times time. And this equation comes from the acceleration. That's where the minus sign comes up. So Vf is equal to Vi plus At is one equation. And that is another equation. And substituting this into this and so on, we can get other equations. The other equations are d is equals to Vit plus half At squared. This is another equation. And then again substituting for time from here into here, we end up getting Vf square is equals to Vi square plus 2AD. So those are equations of motion which will help you in solving problems. Now, how many variables do you see here altogether? If you count the number of variables, how many different variables do you see here? You see initial velocity, you see final velocity, you see acceleration, you see time, and you see displacement. That's it. You have only 5 different variables. Out of the 5 variables, Vi, Vf, acceleration, and displacement are vector quantities. They are the vector quantities, and this is the only scalar quantity. And why do I have to stress on this fact? That's because if it's a vector quantity, you need to be specific about its direction. So if you have a velocity going upward, you have to take it as positive. Anything downward, take it as negative. So this, but for velocities or for acceleration or for displacement, anything upward, take it positive. Anything downward, take it negative. Anything forward, take it positive. Anything backward, take it negative. So if you need to follow these sign conventions in order to work through a certain problem. And I'll show you how to solve problems using this. How do you solve problems using equations of motion? The best way to solve problems using equations of motion is by first analyzing the problem itself. Let's say, for example, if a car was not moving at a stoplight and then it started accelerating. It started accelerating and it picked up a certain velocity of 20 meters per second in a time of 10 seconds. It went from 0 to 20 in 10 seconds. So that's the situation. And the question is asking, what is the displacement? So what we need to do is this. You know that all these equations, how many variables are there in this equation? There are 4. 1, 2, 3, 4. So if you know 3 of those variables, can you find the 4th one? Yes. How many variables are here? 1, 2, 3, 4. Again, if you know 3 of these, you should be able to find the 4th one. How many variables here? 1, 2, 3, and 4. Again, 3 things known, you can find the 4th one. 1, 2, 3, 4. 3 things known, you can find the 4th one. So that is basically the idea of solving problems. So first job that you do here is list all the quantities that you are already provided. Do you know initial velocity? Yes. Do you know the final velocity? Yes. Do you know the time taken? Yes. So we have this, we have this, we have this. 3 things are known. And the question is asking, what is D? So what is the equation that connects these variables? So back again to this. You can see that all the equations are different. All the equations are different. This equation has 4 variables, but something is missing. D is missing. Something is missing here. A is missing. And something is missing from here. That is, final velocity is missing. And something is missing from here, which is time is missing. So if you are given stuff, but time is not mentioned to you, then use this equation. If you're given some variables, but final velocity is not given to you, then use this equation. If you're not given anything about acceleration, then use this equation. If you're not given the displacement, then use this equation. So back to the problem. You are given VI, you are given VF, you are given time, you want to find D. Something is not given to you. What is not given to you? Acceleration. So since acceleration is not given to you, you have to pick the equation that doesn't have acceleration. This is the equation that doesn't have acceleration. So pick that equation up and write it down. VF plus VI divided by 2 times time. And then just faithfully substitute. All you do is just substitute 20 plus 0 divided by 2 times 10. And that becomes 100 meters. That means the car went 100 meters in that period of time. So you can see how the problems are solved. All you do is just use equations of motion. Now, if it is something that's falling objects, so falling objects. For falling objects, the only difference is the object is going to be going upward and downward. So the velocities can be up if it is going up, it can be down if it is going down. For falling objects, you have velocities going up and down. Acceleration for a falling object is always downward. So acceleration is always negative 9.8 meters per second square. Whether it is going up or down, it's always going to be negative 9.8 meters per second square. So acceleration is always pointing down. Even if an object is thrown up and it goes up like that and comes back, the acceleration is always pulling it down, pulling it down. That's why it slows down to 0, and then it still acceleration is in the same direction. Whereas the velocity is upward. So the velocity is upward, 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 0. So velocity is 0 here, and velocity is positive here, and this is the velocity that's negative. But acceleration is always going to be downward. Always acceleration is downward. What is the acceleration at the very top? Still the same thing. Acceleration is always negative 9.8 meters per second squared. Even if the velocity is 0, the Earth is still pulling it down. So this acceleration is created by the Earth's gravity. That's why this is the acceleration due to gravity. So while solving problems are like this, what do? Let me give you a problem. So imagine I'm throwing something up at 10 meters per second. And then this object goes up and comes back and lands back in my hands. How long did it take for it to return back to my hands? That's a question. So I gave initial velocity is 10. I gave you the acceleration because it's always 9.8, negative 9.8. And the question is asking for time, but you need one more thing. And the thing that you already know is displacement. What is a displacement? It was here, now it is here. So the displacement is 0 because it reached the same level. It was here, it reached back here. So displacement is 0. So we have 3 things, 1, 2, and 3, and you want to find the 4th one. What is missing here is a final velocity. So we pick the equation which has no final velocity, which is this. This is the equation which has no final velocity. So we pick that equation up. So final velocity is not there. And so we pick up d is equal to VIT plus half AT squared, and 0 is equal to VIT, so it's basically 10t plus half negative 9.8 and then t squared. That's what you want to find out. So if you simplify this further, 0 is equal to 10t minus 4.9t squared. So if you add 4.9t squared to both sides, we get 10t. Now when you divide both sides by time, one of the times cancels off. So we have time is equal to 10 over 4.9. That many seconds. So 10 over 4.9 is going to be 2.04 seconds. 2.04 seconds. That's the time it takes for it to return back to your hands. So these kind of problems can be done by using equations of motion. Now, going back to the textbook, if you follow the textbook now, you should be able to get a good idea. So here it talks about the same thing, and go through this graph. You can see how the calculation of speed, velocity is done, acceleration, how things are accelerating, and this is like slower speed, faster, and these are, now this is varying velocities. You can see how the velocity is almost zero here, and then it picks up, and that's a constant velocity, and then again zero velocity here, and then again goes down. So you can see how things go. When you drop something from the top of a building, the graph is going to go like this. The acceleration due to gravity can be seen there, and this is showing how the equations are going to be applied. So here are the equations and how the equations can be applied. Now, in the presence of air resistance, when something falls in the presence of air resistance, that will change the acceleration of the graph itself. So okay, now that is showing you something else. So I would advise you all to go through each and every part over here and try to understand the significance of each and every graph. The book also gives you some important equations that can be worked with. Now let me take you to some of these examples before I close this. Typically, an example over here says, a hypnotist watch hanging from a chain swings back and forth every 0.8 seconds. What's the frequency? So the 0.8 seconds is the time period. Frequency can be found out by taking the reciprocal of time period. And then here, a long distance runner has an average speed of 4 meters per second during a race. How far does the runner travel in 20 minutes? 20 minutes, you need to convert it to seconds. 20 times 60, 1,600 seconds. So all you do is 4 meters for 1,200 seconds. So multiply it. 4 times 1,200. So therefore you'll get 4,800 meters. That's the distance run. And then look at this problem here. That tells you the graph shows the distance versus time. Now remember, this is not supposed to be distance, it's supposed to be displacement, because as I said, a distance graph cannot come down. So this is a wrong graph. They put distance, they're showing it's a distance, but then they're drawing a graph downward, which is an impossible graph. So that is displacement. So this is for an elevator as it moves up and down the building. So what's happening here? It's not moving, and now it is moving. Here it is not moving again. It's reached the top. It's not moving, and now it is moving down, and it's moving down to a lower level. You can see that. Now the slope of this line and this line appears to be the same, so which means it should be going at the same speeds. But if the slopes are different, like here, you can see that this one is actually having a smaller slope, and this one is a very steep return. So this is much faster, but it's returning. And this is, oh no, this is the velocity. Okay. If this was a displacement graph, then that's going to be a slower velocity, and that's going to be a much bigger speed of return. Whereas in this case, it's velocity. So the graph of the slope of this line is supposed to be acceleration. So this is going to be, rate of change of velocity is going to be an acceleration, There's no acceleration here, and there is a very steep acceleration there. So I hope things are getting some kind of a shape, and you can actually try some of these problems before you go to the quizzes. It'll give you some idea of how to work these problems out. So you can see a rock is dropped off the side of the bridge and hits the water. What's the velocity as it hits the water? So all you have to do is to apply these equations of motion. You have to apply these equations of motion and answer the questions pretty much like these. Every time, look for the variables, look for which ones are given to you, which one is not given to you, and pick the correct equation, and you should be able to work them out. Now, if you have any questions regarding these, please let me know when I come, or you can email me or remind me. Working these problems should be easy as long as you have followed those all my videos. So that brings us to the close of this, and you should be now capable of answering the quiz questions. So good luck with the quiz questions, and go back to the videos when you want to check again. All right, all the best.